So let's see what's this. Delocalized electrons and their effect on stability, reactivity, and pKa. And this is benzenes and this is cyclohexanes. So benzene and cyclohexanes, electrons that are restricted to a particular region are called localized electrons. Localized electrons either belong to a single atom or are confined to a bond between two atoms. Localized electrons, this lone pair, this bond, and this bond. Localized electrons. Not all electrons are confined to a single atom or bond. Many organic compounds contain delocalized electrons. Delocalized electrons neither belong to a single atom nor are confined to a bond between two atoms, but are shared by three or more atoms. The concept of having delocalized electrons, we talk about delocalized electrons now. Delocalized electron is involved in frequently to explain the behavior of organic compounds. So we are talking about delocalized electrons. Delocalized electrons, what are these guys? Delocalized electrons, the structure of benzenes. To understand the concept of delocalized electrons, we will first look at the structure of benzene, because early organic chemists did not know about delocalized electrons. Benzene structure puzzles them. Oh wow! They knew that benzene had a molecular formula of C6H6. One of the hydrogen is substituted with another atom. Okay, only one product is obtained, and when two of the hydrogen atoms are substituted with another atom, three products are obtained. So this is what they can say. They say C6H6. You replace a hydrogen with the X. So why you get one mono substituted compound, replace a hydrogen with an X, three di-substituted compounds. So this one, 1, 2x2 and x2 here as well. You see there is two hydrogen and other x2, three di-substituted compounds. So this is what they said, but they didn't know the structure. No, this is a modern science where scientists know the structure. A cyclic six-membered ring with alternative single and double bonds. It is a structure that gives the correct molecular formula and give only the product when one of the hydrogen is substituted with another atom. However, when two of the hydrogen of so we see what happens. Book page number 138. So we see delocalized electrons and their effect on stability, reactivity, and pKa. These structures are substituted. 4 di-substituted products are obtained. 4 di-substituted products are obtained. Okay, 4. Their structures are substituted. 4 di-substituted products are obtained. All right. So a 1,4 di-substituted. 1,4 di-substituted. I will show you. This is 1,3. It is 1,4. 1 and 4. This is 1 and 2, 3. And this is 1 and 2 here. So you see double bond here. Is double bond here and here. So 1 and 4. Why double bond here? I mean, if you remove a hydrogen and put a bromine, a double bond is alternative. So alternate double bond because it's a benzene. But bromine 1,4, 1,3 and 1,2 and 1,2 product. This is 1,2 here. So this is 1,2 here. Replace two hydrogen with bromine. So we're talking about these structures are di-substituted. 4 di-substituted products are obtained, and a 1,3 di-substituted product 1 4-disubstituted product and a 2 1 2-disubstituted product. So they're talking about how many substitution is possible. Substituted 4-disubstituted product are obtained. Okay, if you want a 2-disubstituted, there will be 4 products such a 1 3-substituted, which is like this. Okay, and disubstituted 4 being 1 would be like this, another will be here 2, another will be 3, and another will be like this 4, and 1 4-disubstituted 1 and 2 1 2-disubstituted product. Okay, so if 1 2 then 2 product, because the 2 substitutes can be placed either on 2 adjacent carbon jointed by single bond or on 2 adjacent carbon jointed by double bond. Okay, so now we move a little bit further. Yeah, so in 1986, try to make it more clear for you. In 1965, a German chemist, Friedrich Wöhler, suggested a way of resolving this problem, this dilemma. He proposed their nature actually are 4-disubstituted products, but the 2 1 2-disubstituted products convert to rapidly to be separated from each other. So this is, we're reading how people say, So he said like this: there are 2 substituted products by shorter double bond, okay, longer single bond. So this is the they're predicting. Scientists, scientists calculate structures. Friedrich August calculate means calculate structures. So scientists are telling you structures. Means scientists think. You also think, my friends, just like a scientist. Okay. So controversy over the structure of benzene continued until 1930, when modern analytical techniques showed that benzene is a planar molecule, and the 6 carbon-carbon bonds have the same length. The length of each carbon bond is 1.39 angstrom, which is shorter than a carbon-carbon single bond 1.54, but longer than a carbon-carbon double bond 1.33. In other words, benzene does not have alternative single and double bond. If the carbon-carbon double bond in benzene all have the same length, they must have also. If the 1 carbon-carbon bond in benzene all have the same length, they must also have the same number of electrons between the carbon atom. This can be so, however, only if the pi electrons of the benzene are delocalized around the ring, rather than each pair of pi electron being delocalized between 2 carbon atoms. To better understand how electrons can be delocalized, we will now take a close look at the bonding in benzenes. The bonding in benzenes. Each benzene's 6 carbon. Each benzene 6 carbon atom is sp2 hybridized. An sp2 hybridized carbon atom is bond angle 120, identical to the size of angle of planar hexagon. Benzene, therefore, is a planar molecule. Each of its carbon use sp2 hybrid to form 2 other carbon atoms. The third sp2 orbital overlap the sp orbital. So overlap the sp orbital of hydrogen. So we show figure A. This is figure A. We will see figure A first. So this is figure A. The carbon-carbon and carbon-hydrogen sigma bonds in benzenes. A. So this is sigma bonds. Carbon-carbon sigma bond and carbon-hydrogen. B is the p orbital on each carbon of benzene can overlap with 2 adjacent p orbitals. So there is p orbital on each, so they can overlap an adjacent carbon of each p orbitals. So another p orbital, this is another p orbital, and other p orbitals, these are 6 p orbitals. Now C, what is C? C the clouds of pi electrons above and below the plane of benzene. So this is clouds of pi electrons, and this is up and below. This is benzene in between, and cloud is up and below. So this is like a cloud, the pi electrons. And what is this? Green, and in the between you see red, yellow. So this is greenish red. What is this? This is C, and this is D. So C is the cloud of pi electron, and D is electrostatic potential map of benzene. So this is electrostatic potential map. Where are electrons? Okay. So each of the benzene's 6 carbon atom is sp2 hybridized, and sp2 hybridized carbon has therefore a bond angle of 120, identical to size of the angle to a planar hexagon. Benzene's other carbon atoms, the third sp2 orbitals overlap. No angle is look like clear, more clear, yeah. I want to make this one clear, so look like more clear here. Therefore the planar molecule, each of the carbon atom, we want to make it more clear. Okay, so therefore a planar molecule, each of its carbon use 2 sp2 orbitals to bond to 2 other carbons. So each of carbon uses 2 sp2 orbitals to bond to 2 other carbon atoms. The third sp2 orbitals overlap the s orbital of a hydrogen planar. So where we are, let's see. Each of its carbon atom uses 2 p orbitals to bond to 2 other carbons. The third sp2 orbital, the orbitals overlap the orbital of a hydrogen. The third sp2 orbital overlap of a hydrogen orbital of the hydrogen. Like say, so third overlap of the orbital of the hydrogen. Third which orbital? Third p orbitals. Each of the carbon atom 2 sp2 orbitals to bond to the other carbon atoms. So other carbon atoms, they form a bonds. The third sp2 orbitals overlap the s orbital of a hydrogen. Each carbon also have a p orbital at the right angle to sp2 orbitals. So these are p orbitals, they are at right angle to sp2 orbital. Because the benzene is a planar, the 6 p orbitals are parallel, figure V. Because it's a planar, the 6 p orbitals are parallel. The 6 p orbitals are parallel. The p orbitals are closer enough. The p orbital is closer enough for side to side overlap. The p orbital are closer enough for side to side overlap. So each p orbital overlaps the p orbital. So each p orbital overlaps the p orbital. So each p orbital overlaps the p orbital on both adjacent carbons, on both adjacent carbons, on both adjacent carbons. As a result, the overlapping p orbitals form a continuous donut. As a result, the overlapping p orbitals form a continuous donut. As a result, the overlapping p orbitals form a continuous donut-shaped cloud, donut-shaped cloud of electron above and other donut-shaped below. Donut-shaped cloud up, donut-shaped cloud of electrons up, and the donut-shaped cloud of electrons. P orbital overlap with p orbital and both adjacent carbon. As a result, the overlapping p orbitals form a continuous donut-shaped electrons cloud of electron above and another donut-shaped cloud of electrons below the plane of the benzene ring. So another is up, another below the plane of the benzene ring. The electrostatic potential map shows that the carbon-carbon bonds have the same electron density. So carbon-carbon bonds you can see have the same electron density. This is carbon-carbon bonds. So electrostatic map. Electrostatic map mean you can see electron density. So the electrostatic potential map shows the electrons shows that the electrons carbon-carbon bonds have the same electron density. carbon-carbon bond have the same electron density. So each of the 6 pi electrons, therefore is localized neither on a single carbon, neither on a single orbital. Each of the 6 pi electrons therefore are localized neither on a single atom, nor in a bond between two carbon atoms, as in alkene, nor in a bond. Instead, each pi electron is shared by 6 carbon. Each pi electron is shared by 6 carbon. Instead, each of the 6 electrons therefore are localized either on a single carbon atom, neither on a single carbon atom, nor in between two carbon atoms, as shown in alkene. Instead, each pi electron is shared by all the bonds, by all the carbon. 6 pi electrons are delocalized. They roam freely within the donut-shaped cloud that lie over and under the ring of the carbon atom. Over and under the ring. Consequently, benzene can be represented by a hexagon containing either dashed line or a circle. To symbolize the 6 delocalized pi electrons, we write like this: 1, 2, 3, 4, and we are drawing this dotted, or we draw like this. This is representation of the benzene structure. This type of representation makes it clear that there are no double bonds in the benzenes. No double bonds in the benzenes. We see now that Kekulé structures, there are not double bonds. Kekulé structures of benzene was pretty close to the current structure. Actual structure of benzene is Kekulé structure with delocalized electrons like this. So with delocalized electrons. Now we go to another page. Page number 140 of the book. Resonance contributions and the resonance hybrid. A disadvantage using dashed line to represent the delocalized electron. Is that they do not tell us how many pi electrons are present. In the molecule. For example, the dashed line inside the hexagon and the representation of the benzene indicate that the pi electrons are shared equally by all the 6 carbon, and that all the carbon-carbon bond have the same length, but they do not show how many pi electrons are in the ring. Consequently, chemists prefer to use structure with localized electrons to approximate the actual structure that has delocalized electrons. The approximate structure with delocalized electron is called resonance contributor. The actual structure with the delocalized electron is called resonance hybrid. The approximate structure with the delocalized electron is called resonance contributor. The actual structure with delocalized electron is called resonance contributor. The actual structure with delocalized electron is resonance hybrid, and the approximate structure with delocalized electron is called resonance contributor, and the actual structure with delocalized electron is called resonance hybrid. Notice that this is easy to see that there are 6 pi electrons in the ring of each resonance contributor. This is resonance contributor and this is resonance contributor as well. So double bond here, by you put double bond here and you leave one, there are double bond, leave one, there are double bond, 1, 2, 1, 2. But this is other sides. This resonance hybrid, this resonance contributor, this is resonance contributor. So resonance contributor is approximate structure. Resonance hybrid is the actual structure. The resonance contributor is shown with a double bond arrow between them. The double bond arrow does not mean that the structures are in equilibrium with one another. So this doesn't mean that the structure is equilibrium. Rather, it indicates that the actual structure lies somewhere between the structures of the resonance contributors. So what is this? Electron delocalization is shown by the double bond arrows. This one, electron delocalization. Equilibrium is shown by 2 arrows. So this is electron delocalization. In equilibrium, and you see 2 arrows like this, just one-headed. The following analogy of The following analogy, why no the words are very clear. I have no idea how to make them more clear. The following might be like this. The following, trying to make it more clear for you. Actually gone. Oh my god, they're actually now gone. Okay, we wait. Okay, so the following analogy illustrates the difference between resonance contributor and the resonance hybrid. Imagine that you are trying to describe to a friend what rhinoceros looks like. You might tell your friend that rhinoceros look like a cross between a unicorn and a dragon. The unicorn and a dragon don't really exist, so they are like the resonance contributors. They are not in equilibrium. A rhinoceros does not jump back and forth between the two resonance contributors, looking like a unicorn 1 minute and a dragon the next. The unicorn and the dragon are simply ways to represent what the actual structure. The rhinoceros look like resonance contributors, like unicorn and dragon, are imaginary, not real. Only the resonance hybrid like a rhinoceros is real. So first we see what is rhinoceros. This is rhinoceros, so we say there's in between middle unicorn resonance contributor. This is look like a horse, and this is dragon. Is imaginary structure is like this, big tails. So this is unicorn resonance hybrid. That's the actual structure. So we say this is somewhere developed between these two. So just a funny examples. Okay, we go to the next page. Yeah, take you to the next page. Electrophiles delocalization occurs only if all the try to make it very clear, but couldn't yet. Sorry. I will make it clear. Think about electron delocalization occurs only if all the atoms sharing the delocalized electrons lie in close to the same plane. So electron delocalization occurs only if all the atoms sharing the delocalized electrons lie in close to the same planes, so that pi orbitals can effectively overlap. For example, cyclotetraene. This is cyclotetraene 1, 2, 3, 4, 5, 6, 7, 8. Cyclotetraene, for example, cyclotetraene is not planar. It's sp2 carbon. Carbons have the bond angle of 120. sp2 orbitals, these ones. This is sp2. So is sp2 carbon atoms bond angle 120, and a planar 8-member ring would have bond angle of 135. Because it is not planar, the p orbitals cannot overlap. So it's talking it's not planar. Cannot overlap p orbitals. Each pair of pi electrons is localized between two carbon instead of being delocalized. So this is here localized, and here this is not delocalized over the entire ring of 8 carbon atom. Thus the cyclotetraene, unlike benzene, has alternative single and double bonds. So this is alternative single and double bonds, but it's not planar. 1, 2, 3, 4. So this bond is bigger bonds, and this is electron density map. This is 3D molecule. Cyclotetraene is 3D like this. Drawing resonance contributors. We have seen an organic compound. The delocalized electron is generally represented as a structure with localized electrons. to let us know how many pi electrons present in the molecule. For example, nitroethane. For example, nitroethane is represented having a nitrogen oxygen. For example, nitroethane is represented having a nitrogen oxygen bond and a nitrogen oxygen single bond. So you see, first thing is nitrogen oxygen bond, where is nitrogen oxygen, and then nitrogen oxygen single bond. So double bond, single bond, we're talking about one lone pair, another lone pair, two lone pair. Here's two, three lone pair, just one bond. So nitrogen has given electron to form this bond. Okay, this is nitroethane. Actually, however, the two nitrogen oxygen bond and the nitroethane, two nitrogen oxygen bonds are identical. They each have the same bond length. A more accurate description of the molecule structure is obtained by drawing the two resonance contributors. Both resonance contributors show the compound with the nitrogen oxygen double bond and the nitrogen oxygen single bond, but show that electrons are delocalized. The double bond in one carbon contributed is the single bond in another. So this is resonance contributor, double bond here and double bond here. So we're just changing, bonds. This electron just come here and form a double bond here. So the reason hybrid shown that p orbital, the reason hybrid shows, the resonance hybrid shows, shows that the p orbital of the nitrogen overlap the p orbital of the each oxygen. So nitrogen overlaps the p orbital of each oxygen. In other words, the two pi electrons are shared by three atoms. The resonance hybrid one, and also shows that two nitrogen oxygen bonds are identical, and that the negative charge is shared by both oxygen atoms. Thus, we need to visualize and mentally average both resonance contributed to appreciate what actually molecules resonance hybrids look like. So this is like this. Negative plus, this is negative resonance hybrid. Yeah. So this is actually what it looks like. Delocalized electrons result from p orbital overlapping the p orbital more than one adjacent atom. Okay. Now we will finish this topic. Rules for drawing resonance contributors. To draw resonance contributors, the electrons in one resonance contributors are moved to generate the next resonance contributor. As you draw resonance contributor, keep in mind the following constraints. Only electrons move. The nuclei of the atom never move. The only electrons that can move are pi electron in pi bonds, and lone pair electrons. The total number of electrons in the molecule does not change. Total number of electrons in the molecule does not change. Therefore, each of the resonance contributor of a particular compound must have the same net charge. If one has the net charge of 0, all the other must have the net charge of 0. A net charge of 0 does not necessarily mean that there is no charge on any of the atom. A molecule with positive charge on one atom and a negative charge on another atom has a net charge of 0. Notice as you study following resonance contributor, then what resonance contributors are drawn. The pi electron lone pair are always moved towards an sp2 carbon. Remember that an sp2 carbon is either positively charged carbon or a double bond carbon. Electrons cannot be moved towards sp2 carbon because sp3 carbon cannot accommodate any more electron. It has complete octet. The following carbon atom has delocalized electrons. To draw the resonance contributor, pi electrons are moved towards positive charge. The resonance hybrid shows the positive charge is shared by two carbon. So positive charge is shared by two carbon, one this one and this one. These electrons moving here, resonance contributed. When these electrons move here, they form a double bond and plus charge here. So this is resonance hybrid, meaning we will draw double bond here and double bond here, dotted and plus charge on this, plus charge another. Now let's compare these contributors with a similar compound in which all the electrons are localized. The pi electron in the following compound cannot move because the carbon they would move in is sp3. sp3 carbon cannot accept electrons. So here they cannot move because this is sp3. So this is localized electrons. sp3 hybridized carbon cannot accept electron. In the next example, pi electrons again move towards a positive charge. The resonance hybrid shows that positive charge is shared by 3 electrons. So pi electrons moves here, and when it moves here, positive charge will be where then? Here I see the positive charge. These double bond, no, because when these electrons here, there would be positive charge. It will build up here, okay, because they form a double bond here, as you can see. So this positive charge, now this electron moves further, and you will see positive charge here. Yes, that's right. Positive charge here. Now further, one double bond here, double here, we put odd 1 2 3 4 resonance hybrid. So one, this one, these two, so you can see 1 2, but other 2 bond as well, which you got later. I mean these ones. Yes, so next to, so this is a resonance hybrid. Okay, we're going to finish this chapter about resonance. Okay, the resonance contributed for the next compound is obtained by moving lone pair electron towards sp2 carbon. The sp2 carbon can accommodate the new electron by breaking a pi bond. So sp2 carbon can accommodate the new electron by breaking the pi bond. You see here it forms a double bond, and these electrons move here, so you will see 1 2 3. This is negative charge. Yeah. Okay, this is resonance contributed. Okay, resonance contributed. So this is you see is double bond, dotted, and negative charge here. This was plus. So resonance contributed like this here. 1 2 3 6 electron, but these electrons, pi electron, go here. So this is resonance contributor, resonance hybrid. Following resonance contributors are obtained by moving pi electron towards a sp2 carbon. Notice that electron move towards the most electronegative atoms. So these pi electrons move here, you will see plus charge here and double bond here, and then when these electrons move towards oxygen, single bond, and oxygen would have negative charge and 6 total electron, 3 pi, 3 lone pairs. So hybrid, resonance hybrid here, resonance hybrid, dotted, just put. Radicals can also delocalize electrons. Resonance contributors are obtained moving the unpaired electron towards an sp2. So unpaired electrons, this is not pair, this is not pair, so towards sp2 carbon. Unpaired electrons, resonance contributors. So this is if we move this one here, here this is dotted here, everything. So this is double bond like this. So this bonds, these 2 electrons, one go here and form a double bond, and this one, this